So good morning everyone. We're in session 2. So today we will study finite differences. Well, this is the outline again, so that you still have in your minds the big picture of the course. And today this is gonna be our main focus. If you remember the tasks of last week, okay, we first learned how to, from a integral perspective, to derive a partial differential equation, a convective diffusion reactive equation, if you remember. And also we just, by using very simple one-dimensional systems, we'll be able to code in MATLAB the analytical solution of those equations, and we will be able, and we were able also to create some little animations. I hope they are already in Moodle, by the way. And that was our first approach in coding and some equations of this world. Today we will, for the first time, start with the numerical discretization of an actual partial differential equation, okay? And we will start with one of the most useful and most simple PDEs, which is the heat equation. To give it a little touch, which is a little bit more nice, more fun, is to be able to have a conductivity inside the heat equation which is not uniform. So you will see here, for example, that the isolines of temperature at some point somehow they get like deviated because you have a solid in the inside with a different conductivity. We can have also finite volumes. This is gonna be the subject of a study next class, and the next, the one after that one. And this is gonna be very nice because it's with unstructured grids, and this is something I will tell you next time. Is the way we decide we study finite volumes in this course is particularly complete, and you give really feeling of what is this, and the Green's functions eventually in the last class. Also to remind you that we will have a session devoted to study how to solve a linear system, how to make it first sparse, so in terms of like express it as a sparse matrix to avoid dummy computations and to make things more efficient, and to be able to understand how you can see from a physical world to see the system in a mathematical world in terms of computational matrices. And also this is something you will see in the next in the fifth session. Once we have been exploring this spatial discretization of the equations, we go and we add time. Ladies and gentlemen, we have here a grid, a one-dimensional grid, two-dimensional grid, and a three-dimensional grid. We have that grids actually are composed by cells. In this case, we have a cell which is three-dimensional, one-dimensional cell. And here the cell is surrounded by, well, the faces, and the faces are intersected and form nodes. So this is what composes a grid. Here we see a very simple grid because we have just a straight line, a square, and a cuboid. And this is actually very classical of finite differences, because in finite differences the idea is that all faces are aligned with the frame of reference. Since in this case we are having a Cartesian frame of reference, then we have actually Cartesian grids. We could also have polar coordinates, and then we will have, instead of cuboids and squares, we will have maybe a circle and a cylinder. Or the same thing with the spherical coordinates. We will have maybe a sphere. So the advantage of this is that the simplicity is maintained in terms of the geometry, But then the schemes that are derived from finite difference can have any order of accuracy you desire. So you just have like a very simple recipes using Taylor expansions when you can just go very high, 10, 12, 15th order of accuracy if you want. You can also have non-uniform grids. It means that you can have like cells with different sizes, and you have actually your numerical scheme for that. You can also use the nodes when you, for example, if you want to have a node that where the information comes from the surrounding, then you can have a centered scheme. But if you want to have a numerical scheme depending only on the information coming from one side, then you can have, for example, upwind scheme or downwind schemes, and so on. It's very flexible. But it's still, we have to consider that the geometries are very simple. I have heard that you can also have customized frame of references depending on the system of your interest, and therefore you can actually maybe have something complex. But I don't know how general is just. So I would say that finite differences is somehow very efficient for simple geometries. It's still very useful in research when you want to study turbulence sometimes, or phenomena that require, for example, very low dispersion and dissipation, then you have actually finite differences. So to introduce the concept of finite difference, then we have just to define what we want to approximate. So the first thing we want to approximate, which is just the derivative of a given quantity. You can think this as a scalar, let's say a temperature, for example, in the derivative with respect to a direction, which is the x. So we can also proceed in the same way for high order derivatives. Normally, partial differential equations for fluids are first, second, third. I haven't, maybe third sometimes, but this is what is common. And what is this about? So the idea is that we will be placed at the node P. So we are standing here, and we want to know as much as we can at this position. So what is the derivative of the phi dx at this position? We have the information of the value of phi. Let me call temperature from now on. We know the temperature at E, we know the temperature at EE, at west, and at west. We know the distance. So in this case, it's just a given distance. It can be different from node to node. But the main idea here is to say that the expression of this derivative is going to be given by a linear combination of the information of the temperature at these points. Okay? This is the idea. We have assumed we have a flow in this direction. This is just in terms of like have a convention to know, to give some labels, some names. So we will call first a central scheme. If I'm standing at P and I have the information at these 2 points, but also at these 2 points, so it's like I'm in the middle. So I will be able to have like a symmetric evaluation of the operators, of the derivatives, because I have the same information from the left than from the right. So this is going to be called a centered scheme. However, this is not always the situation. You may have the situation, imagine that you have, let me just, something here. Imagine you have, you're placed in P, and this is just doesn't exist because your domain is this one. So this doesn't exist because you are at the boundary. So it means in this example that you cannot have information coming from the right because there is nothing. Then your information is coming only from the left. So in that sense, you will have information which is up, so from upstream, and that's why this kind of a scheme is called upwind, because it makes use of the information that is on disposal that happens to be only upstream from P. Okay, and the contrary example is when you are in this domain and you don't have access to this information because it doesn't exist, so it's just the opposite. Then we will have a downwind scheme. Okay. Okay, so let's do the example of the downwind scheme. Okay, so we are at P and we have the information of E east and E east here like this, and this doesn't exist. So what do we want to know? We want to know which are the values of these A coefficients. Once we know the values of these coefficients, we will be able to have a numerical scheme for the derivative of phi. So we go to the blackboard right now, which is a virtual blackboard, you already know from the last class. Okay, so the example I just gave for this downwind scheme for the first order derivative of a quantity phi. So to make it more physical, we will call this phi t, as I told you. So we have here, I will just put it here at the top. This is supposed to be the node, 1 node, 2 node, 3 node, and so on. And we will call this the node P, the node east, the node E east. I think we don't have information in there. I mean, this is maybe doesn't suffice. It's like this. Okay. And we want to do the approximation. So the first, we will just write in here. We have the temperature at P, the temperature at east, and the temperature at E east. Okay. So the first thing to say is that we will do a very, let's say, rough approximation of Tp given the information of TE and TEE. So, but we are standing at P. So this one is going to be trivial. So it's going to be Tp is equal to Tp. So this is trivial. What it doesn't seem too trivial is when I do this. When I say, yeah, T is approximately Tp and TE is approximately Tp. Okay, this is a very, very, very rough approximation. Okay, that's why this third order Taylor expansion is completely insufficient. So let's go and let's add the first order. So we will have the coordinates of x east minus xp, and then we will have dp dt. So when I do this, oh my god, what I'm doing here. So the nice thing of having classes when the students are there is that they point out the mistakes I do. Okay, so just do the same. At least in your minds, you will create some discussion. This is the bad thing of virtual classes, but we'll have something, some discussion in the next meeting when we all meet. Okay, so this is the first term, and someone will ask me in the students if that's correct, it's enough. Otherwise, maybe we can go to the second order. What happened? So the second order is gonna be x e minus xp. What is this? Square dt dx. Okay, and this is the second order. And something that someone should point out is, okay, but is dt dx evaluated where? Think, yeah, evaluated at P, because we are standing at P and everything is related to P. Okay, and then we can go beyond this and write an additional term which is gonna be what? 3, and this is 3. So you already realize something is missing here. What is missing? Think. So what is missing is that this factorial term, isn't it? So here is supposed to be 2 factorial. Here is supposed to be 3 factorial, which is 6, and so on. Okay? So this is the approximation of this term, of t. Now I will do the same for this one. Okay, and the nice thing with these virtual classes is that something just pop up. So the third question is related to, so it's exactly the same as before. The only difference is that the distance here is different. It's with respect to EE. Okay? Well, now we will sum these equations. This is a plus here, and I will write very small. So TP plus T plus T. Remember that we want at the very beginning, maybe I didn't write it down, but it's important I write it down. We want to have TP as A P TP. Wait, this is the T dx. So this is the objective. The T dx at P plus AE TE plus AEE TEE. So this is what I want. So since I want that, I will now multiply the first equation by AP the second equation by AE this is an AE, and the third equation by AEE okay. Now the sum of this, okay, this is something also to realize. We will never have something that is equal. For equal, we will need an infinite amount of terms, but we have something that is very accurate, or maybe very approximation, okay, of this. So if we sum this, we will have something that is supposed to be dt dx p. And now I will just sum the rest of the terms. So we will start with TP AP plus AE plus AEE. I'm sure that some of you will just go forward in this video until I finish this. Maybe I should do that as well. Okay, before continuing with the rest, I wanted just to make you aware that this derivation is general. It means that we can have a distance that from xe to xp is not the same as the distance between E and EE. Doesn't have to. So we can consider non-uniform grids in that sense, okay? Now, for the sake of simplicity in terms of the explanation and the derivation of the equations, we will introduce now an assumption. But remember that it's not necessary for if you want to capture the derivation of this derivative for non-uniform grids. But the assumption that we will do is that here we will have a distance that is going to call delta x, and that it happens to be the same as here delta x, okay? So in that sense, everything got simpler for the equations and for the explanation. Okay, so this means that this term here becomes delta x, this one becomes delta x over 2, this one here becomes delta x over 3 over 3 over 6. And now this one, what is this one? So this is normally I ask this, and the guys in the first row, who is in the first row right now? No idea, maybe everyone. So you will answer 2 delta x, okay? This one, okay, now it's a little bit complicated to write it down, but this is gonna be 2 delta x over to the 2, so you mean 4 delta x over 2, which means 2 delta x again. So let me just write it down. Okay, I will just erase this thing. So we'll have 4 delta x squared over 2, and this one is the same, so it's gonna be to the 8th, so to the 3rd, so this is gonna be 8 delta x over 6. Okay, so now we will continue with our factorization here in this part below. So this is gonna be ae delta x plus 2 delta x ae Okay, so suddenly we have the whole expression. Okay, so we have 4 terms in the right hand side of this equation, as you can see here, 3rd, 4th. Okay, what do we do now? We have to now just solve the equations. Which equations? So we have first to define the equations, and the equations are this one. So we need a condition for this sum, we need a condition for this sum here, we need a condition for this sum and for this sum. So you are behind your screens, you have to think which are the conditions that we want to impose. So we can impose, we need this one to be equal to this, so that in order that it happens, we just put here 0, we put here what? Okay, this one is also 0, this is also 0, and this is 0. No, that is actually 1. This is the term we want, so this term is actually equal to this one. Okay, I will go to the next slide and write these equations again. Okay, so I will write the equations again. So we have AP plus AE plus AEE equals 0. Okay, so we go in the future time. Right now we have everything. See, we have 4 equations. We have 4 equations, and we have how many unknowns? Think. We have AP, AE, AEE. We have 3 unknowns, and we have 4 equations. What do we do? So we have a overdetermined problem. So someone could say, yeah, just do some least squares, do some linear optimization, and then you just get an approximation value for AP, AE, and EE. Okay, this is actually not what we are going to do. The best that we can do is just to select the 3 main equations, the 3 more useful equations to solve, because we in order to solve with an exact value AP, AE, AE, we need only 3 equations. So I can ask you, okay, this equation has to be there for sure. And now we need 2 from this, this, and this. Which one would you choose? Okay, then maybe someone is thinking behind the screens, which one is giving me less error? And this is actually the way to think. If I ignore this equation and I choose to solve these equations, that would be a terrible mistake, because this equation is assuring me that this term is going to be 0. And remember that each term in the Taylor expansion is associated to a given order. So it means that this is going to be a zero order, a first order, second order, third order. So this term is crucial. And if we want it to be 0, this equation has to be satisfied so that the truncation error at this order is 0. Okay? So this has to be there. So this has to be there. And which is the one that is give us less truncation error in that sense. So this one, if we ignore this one, is more catastrophic than ignoring this one, okay? Because this is third order and this is fourth order of occurrence. The truncation error is associated to a fourth order. So that's why this is gonna be, we will have to live with this, okay? And this is going to be associated with our truncation error. This and the high order terms in the expansion. So by saying so, we will select these 3 equations to solve these equations. Okay, so maybe some of you will be lazy, but why not just to have some exercising this morning? So just try to solve these equations by hand. Okay, well, you can pause the video and solve them. When you have solved them, you realize this. So the first is gonna be A1. Oh, let me just put another color. A1, or let's say AP, sorry, AP is equal to minus 3 to delta x. AE is equal to 2 over delta x. AEE is equal to minus 1 over 2 delta x. This is also parentheses here. And this is the result of the equations. Okay, so you can express everything as the linear combination, remember, which is nothing but saying minus 3 minus 3. Okay, I will just write here 2 delta x in the denominator so that everyone is happy, not confused. Put white in here. So 2 delta x. And here is actually, remember that the Taylor expansion or the linear combination of terms, I will write it in here. So dt dx at p here is approximated a p tp plus a e t e plus a e e t e e. Okay, so now we want to multiply ap by tp, then plus 4 te, then minus 1 tee. And the truncation error. So you now think which is the value of delta x. So you can see here third, and you may make the little mistake of putting here 3 and say, oh, okay, so we have here an approximation of the derivative, which is third order accurate because we have the truncation order is of order 3. And that's wrong. Because remember that if we see these terms here, AE, AEE, they have a denominator with delta x, okay? So you replace this in here and this one in here, you will end up having a delta x to the square, not to the delta cube, okay? So it means that the truncation error actually is not third, but is second order. And that leads to say our numerical scheme for the derivative at p is second order accurate. Okay, so we come back to the slides and we visualize here the expression of the derivative of phi with respect to x. Now we have here an equality because we have added the truncation error in the expression. Remember, we just said is second order accurate. So you realize that taking into account 3 equations, we were able to obtain a numerical scheme which is second order accurate. Now, you can presume that if you add an additional equation, so if you have an additional information from an adjacent node, let's say, for example, here x, e, 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 or something like that, then you will be able to increase the order to third, and eventually to fourth, to fifth, if you actually keep increasing nodes in the vicinity. So perhaps then you will ask, yeah, finite difference is very appropriate to derive numerical schemes of any order. So if we have the opportunity to have 10th order of accuracy, 12th order of accuracy, why don't we do it? Let's just do it. Maybe to be more exact. Okay, so the answer is actually as any answer in engineering. In engineering, is everything's a threshold. So you have to see the cons and the pros as well. So yeah, you can increase the accuracy. So as you reduce the mesh, for example, the error will go faster to 0. Okay, but do you need it really? So you will see that for diffusive problems like the one given by the heat equation, you don't really need to have very high order of accuracies. You can have very reasonable results, very accurate results actually, with second and third order of accuracy without trouble. However, there are cases when you want to explore for example, propagation of acoustic waves. Then, if you want to avoid dispersion or dissipation of the acoustic waves, you may want to have very high order of accuracies in your numerical scheme. Okay, very high, I mean something like 10th, 6th to 10th, something like that. Okay, so depending on the physical problem of interest, you will use the numerical accuracy, the proper numerical accuracy of your needed. This is one thing. The other thing is that as you go higher in the order of accuracy, you will have more unknowns. Now, just to make mention in here, so we have in this case 3 unknowns. So we need, when you solve the equation, you will have the temperature at P, temperature at east, temperature at E east. And if you actually write this equation for every single node, you will realize that the computational matrix is something, let's call it A. So you will have a square matrix, then you have the diagonal, in this case P, maybe some also off diagonal terms. If you will have a centered scheme, then we can have something like this, and this is the matrix that describe the links of the nodes in the system. So if you have a second order of accuracy, like in this example, for this downwind scheme, then we need 3 unknowns. So maybe this is gonna be more clear in the at the end of the class. But anyway, so you may have every single row is an equation for a node. Okay, so in this case we will have 3 nodes that are linked. If we increase the order of accuracy, basically it means that we will need more terms, so that are linked. So basically you can actually add diagonals to the matrix as you increase the order of accuracy, which means that the sparsity of your system decreases, so the matrix become more dense, and then you won't have like this computational efficiency that matrices with a very small amount of diagonals offer. Okay, so this is always a threshold. So you want to have something accurate but maybe numerically expensive, or something that is not as accurate but computationally efficient. So as I told you, for the heat equation, that's fine. A second, third order of accuracy is fine. Okay, so maybe you can go back later, because this is a video, supposed to be a video, so you can come back and see once you have understand the last part, when actually I show you how to build the finite difference, an example to build a matrix from a two-dimensional domain of a trivial equation. Okay, and just to point out, these are just diagonals, no? They are a little bit like too wiggly in here, but this is just for some basic explanation. Okay, so this is about the order of accuracy. So as pointed out, so you saw that the numerical scheme we derived was a downwind scheme with an uniform mesh, because we use delta x just as the distance between any two nodes. But remember that you can actually use what we just learned to derive centered schemes, upwind schemes, and you can also consider grids that are not uniform if you want. You can also go and check how the numerical scheme of a second order derivative is as well. So the procedure based on this Taylor expansion is just general. You can do anything. In the class, we will just focus on center scheme, upwind scheme, and downwind scheme. These three, and we will be applying always second order accuracy. Okay, so let's just formalize this understanding of order of accuracy. The accuracy order of a FD discretization is the power of delta x to which the truncation error is approximately proportional. So here it is an example. We have two order of accuracy. This is first order accurate, this is second order accurate. This is the one we just derived, and this is something that you might have already seen before somewhere else in another class, which is very basic, just considering two different nodes. So what does it mean, the order of accuracy? So just imagine you have exactly the same mesh for this case and for this case, so the same size of the delta x if you want, and you do your discretization and you get the results for the problem you are looking at. And then you do the same, but now you will reduce the mesh size by 2. Now you will have a more refined mesh in the two cases. Okay, what happens is that the error decreases in both cases, but the error decreases in this case much faster. In here it decreases, let's call it linearly, because it's proportional to the delta x to the 1, but here it decreases quadratically. The error decreases quadratically because it's decreasing as delta x to the square. So basically is, if you have, let's say, this hypothetical example where you decrease the size of the mesh until you have a very infinitesimal distance delta x, you will see that this numerical scheme will go faster to 0 than this one. So that's why when a refinement will show up faster in this numerical scheme than in this one. So the consequence of a refinement in the results is what I meant. Okay, now we introduce another concept which is called consistency. A numerical scheme is consistent as long as the truncation error tends to 0 when delta x tends to 0. So basically that the numerical scheme is unbiased. So we go to the same example as before. So we have the first order accurate, second order accurate, and think that we are able to decrease the size of delta x. So we refine the mesh several times, and you will see that, yeah, okay, this one goes faster because the order of accuracy is higher. But anyway, this one, both of them will go to 0. Both of them, okay? So both of these, the two schemes are consistent. If we had a inconsistent or a numerical scheme which is not consistent, we would mean that we will have like an epsilon. When we go to delta x goes to 0, still the error will be there, and that will be non-consistent. Okay, so basically any numerical scheme that works somehow properly must be consistent. So we go now to the last slides of today. So we remember from the first class that we had this unsteady, convective, diffusive, reactive partial differential equation. We will now focus on an elliptic problem which is defined by the heat equation. So let's see what I want to say with that. So the first thing we will do is that we will eliminate any flux, any convective flux from the equation. So we don't have any velocity of the carrier fluid, and the unsteady term is also removed. So we care only on the steady solutions. And additionally, okay, so this is the equation we will end up having. Here there is actually I never realized about that before. There is a mistake here. We need here a minus sign actually. Maybe some of you already pointed out. So this is the equation. We can do something else in addition to make it simpler. So we see here we have the thermal diffusivity and the density. Now we will express phi to be the internal energy, which is in turn given by the multiplication of the heat capacity C times the temperature. So we will have here Ct, and this C is gonna go out from the spatial operator because the heat capacity is considered to be constant in space, and then we can express this definition of the heat conductivity, which is nothing but thermal diffusivity times density times heat capacity, and we end up with the heat equation. And things can be much more simple if we consider in turn that the heat conductivity is constant in space. In that sense, lambda goes out from the spatial operator, and we're having, let me just write this down here. So if lambda constant in space, well, in time as well, then we will have minus lambda okay, like this, and this is the source. Okay, so this is gonna be the problem we will do today. I will provide you with nothing actually. I will just show you some small template in my lab, which is basically nothing. It's just 3 lines, because you will have the challenge of do everything by yourself today. Okay, from what you know, from what we will discuss on the class before starting the actual exercises. I will give you some hints on my lab and so on. But basically the idea is that we will model a square. We'll model a square like this, and we will impose 3 types of boundary conditions. We will have an isothermal wall, and we will introduce here, for example, the temperature of the surrounding fluid, let's say air. We will have a wall here that might be adiabatic, so here the heat flux is going to be 0, or you can impose an actual heat flux which is not equal to 0. And the idea is that at the end you will obtain something like this when you have this distribution. So you can think this as an example of a fin. When you have here temperature that you want to dissipate, the corresponding heat, and the heat will flux in this direction outwards, and you will obtain the corresponding distribution of temperature. Additionally, you can consider to have a source of heat somewhere, and this source is basically super easy because you can just impose a collection of points as non-zero elements of a vector S in here. This is something we will see, or you will also play with, resolve with, and that's all. So remember here, this is something I want you to have in mind, that Okay, I forgot again. Sorry about this little sign here. It's important. Okay. Well, so let's meet in the next class. We can also discuss about the projects, as I told you last time. This is super important. It's one of the main objectives of this class, is to be able to have very nice, interesting projects, something you really feel is yours because it's beautiful. Okay. Okay, so thank you very much, and let's see on Friday. Bye bye.